In March 2026, NASA overhauled the Artemis program under the Ignition initiative. The agency redirected its entire focus away from cislunar orbital stations towards establishing a permanent, enduring presence directly on the lunar surface. The initial spaceflight strategy relied on a multi-billion-dollar orbital outpost known as the Lunar Gateway. This station was intended to serve as a staging point where astronauts and cargo would aggregate before descending to the Moon. The Gateway was designed to operate in a near-rectilinear halo orbit, or NRHO. NRHO is a highly elliptical orbit that balances the gravity of the Earth and the Moon to minimize station-keeping fuel. However, because the apogee of this orbit sits extremely far from the lunar surface, any vehicle departing the Gateway incurs a massive mechanical penalty. It must burn vast quantities of cryogenic propellant simply to reach low lunar orbit before it even begins its powered descent. When NASA selected high-capacity commercial systems like SpaceX's Starship and Blue Origin's Blue Moon, this fuel constraint became a critical flaw. These highly massive landers burn so much propellant breaking out of the NRHO that the orbital station effectively acts as a logistical hurdle rather than an asset. Acknowledging this bottleneck, NASA indefinitely paused the Gateway program. The agency immediately reallocated the station's hardware, its international commitments, and its $20 billion budget directly to the construction of a 3-phase lunar surface base. Bypassing the orbital station was a strict physics requirement. Eliminating the massive translunar descent burn is the only way to enable the heavy cargo payloads necessary for continuous surface operations. To accelerate the deployment of this surface infrastructure, NASA ruthlessly pruned its launch dependencies. The agency canceled the near-term transition to the Space Launch System Block 1B, a variant that would have required the multi-year development of a new exploration upper stage designed to co-manifest crew alongside heavy cargo. Instead, the mission manifest is now standardized entirely on the existing SLS Block 1 architecture. This specific launch vehicle will be used exclusively for transporting the Orion crew capsules safely out of Earth's gravity well. By stripping cargo from the SLS, NASA transfers the entirety of the deep space logistics burden onto commercial providers. Vehicles like the Starship Human Landing System will serve as the primary cargo arteries, delivering the massive monolithic structures required to build the base camp. This new architecture requires immediate, rigorous testing. Artemis 3, originally slated as a deep space lunar landing, has been repurposed into a low Earth orbit systems test. Orion will remain near Earth to execute rendezvous and docking maneuvers with the Starship lander, validating in-space fuel transfer and life support protocols without the risk of a deep space landing. Once these logistics are proven, engineers face the challenge of deploying the habitat itself. NASA mandated that the already constructed Gateway orbital modules, specifically the Habitation and Logistics Outpost, or HALO, must be repurposed for the surface. This requires extensive structural retrofits to prevent the pressurized hull from deforming under sustained 1/6 gravity and to protect critical thermal radiators from highly abrasive lunar dust. By standardizing the launch manifest and repurposing orbital hardware, NASA traded the sequential, measured rollout of cislunar stations for raw commercial lift capacity. The agency accepted the high logistical risk of relying on unproven heavy landers to drastically compress the timeline for establishing a permanent base. The Artemis base camp is targeted for the lunar South Pole, an environment defined by extreme thermal contrast. Elevated crater rims experience near-permanent sunlight, while the deep, permanently shadowed craters plunge to temperatures near absolute zero. Initial phases will utilize advanced solar arrays placed on these illuminated ridges. However, solar generation is completely unreliable for sustaining life support or conducting heavy mining operations inside the pitch-black craters, or surviving the prolonged 14-day lunar night. To solve this energy deficit, the Department of Energy and NASA issued a mandate to deploy a 100-kilowatt fission surface power system by 2030. Active nuclear fission provides the high power density required for continuous, resilient operations regardless of sunlight. Operating a fission reactor on the Moon introduces extreme thermodynamic hurdles. Because the Moon lacks an atmosphere, convective cooling is physically impossible. The reactor must reject massive amounts of waste heat purely through thermal radiation, utilizing highly specialized, deployable radiator panels. These cooling panels are highly vulnerable to the local terrain. A microscopic layer of abrasive, electrostatically charged lunar regolith can coat the panels. This effectively acts as a thermal insulator, severely reducing the radiator's efficiency and risking a critical reactor shutdown or core damage. To minimize radiological risk and bypass construction complexities in a vacuum, the entire reactor must be fully assembled and fueled with enriched uranium on Earth. It will then be transported whole via a commercial heavy-lift lander and activated remotely. Mastering high-density heat rejection in a vacuum dictates the success of the entire architecture. Without uninterrupted nuclear power, the energy-intensive industrial processes required to expand the base simply cannot function. For the settlement to be viable, it must implement in situ resource utilization, or ISRU. ISRU is the practice of extracting and processing local materials into usable products. Launching heavy consumables like water and oxygen out of Earth's deep gravity well costs thousands of dollars per kilogram, making reliance on terrestrial resupply mathematically prohibitive. NASA plans to implement a series hybrid architecture for resource extraction. The first phase uses the base's nuclear power grid to extract water from icy regolith mined in the permanently shadowed regions. Through controlled thermal sublimation, the ice is vaporized, purified, and then electrolyzed into hydrogen and pure water. Instead of discarding the leftover dry regolith tailings, the architecture feeds them directly into a second process known as carbothermal reduction. The bulk of the lunar surface consists of silicate minerals that are rich in bound oxygen. In the carbothermal reactor, these dry rocks are heated to temperatures exceeding 1600 degrees Celsius in the presence of a carbon source like methane. This extreme heat physically separates the bound oxygen from the rock, allowing it to be captured and processed into liquid oxygen. By processing the same excavated material twice, this dual-path method maximizes the bipropellant yield per ton of rock. This efficiency is absolutely critical because it directly reduces the intense mechanical wear and tear on mining rovers, which frequently fail due to dust infiltration. To ensure these complex pilot plants reach the surface reliably, the architecture integrates the European Space Agency's Argonaut lander. Launched on the heavy-lift Ariane 6 rocket, Argonaut provides a fully independent, redundant supply chain capable of delivering 1,500 kilograms of specialized ISRU cargo. By mastering the extraction of local water and oxygen, the Artemis program severs its logistical tether to Earth. This capability transitions the Moon from a site for brief scientific exploration into a self-sustaining industrial supply chain. The acceleration of this lunar infrastructure is driven by direct geopolitical competition. The space agencies of China and Russia are aggressively pursuing the International Lunar Research Station, targeting the exact same strategic reserves of continuous sunlight and water ice at the lunar South Pole. The 1967 Outer Space Treaty explicitly prohibits nations from claiming sovereign territory on celestial bodies. However, it does permit the extraction of space resources, and it mandates that nations must avoid harmful interference with each other's equipment. This legal framework creates a massive loophole regarding the 100-kilowatt fission surface power system. Operating an active nuclear reactor requires strict thermal and radiation safety perimeters to protect surface electronics and crew. Because the treaty prohibits harmful interference, these safety perimeters project a legally protected barrier outward from the reactor, physically isolating the most valuable, resource-dense ridges. In practice, these perimeters function as de facto keep-out zones. Whichever coalition lands high-value infrastructure first earns the right to dictate these boundaries, effectively granting them territorial exclusivity over prime real estate. The 2030 deadline for NASA's nuclear reactor acts as a strategic mechanism to establish customary international law. By landing first, the agency secures the power to dictate these boundaries before rival coalitions can monopolize the lunar South Pole. The Artemis base camp is ultimately designed to serve as a high-fidelity proving ground. The hardware, life support protocols, and radiation mitigation strategies validated in the harsh lunar environment form the direct technological lineage for human expeditions to Mars. To bridge the gap between cislunar space and interplanetary transit, NASA announced the Space Reactor 1 Freedom mission, scheduled for launch in 2028. This will be the first active nuclear-powered spacecraft in human history since 1965. This diagram outlines SR-1 Freedom's use of nuclear electric propulsion, or NEP. NEP systems convert the reactor's immense thermal output into electrical power, which is then used to drive highly efficient ion or Hall effect thrusters. This architecture provides extraordinary mass transport efficiency, easily overcoming the severe weight and range limits of traditional chemical rockets. Upon reaching Mars, SR-1 Freedom will deploy the Skyfall payload, a fleet of advanced autonomous helicopters equipped with ground-penetrating sensors. These drones will scour the Martian surface to locate subsurface water ice, scouting the precise landing sites needed for future crewed arrivals. By dismantling the artificial requirement of orbital stepping stones, the 2026 Artemis overhaul focuses entirely on the realities of surface habitation. Mastering the extremes of thermodynamics and geopolitics at the lunar South Pole delivers the precise technological blueprint required to expand humanity across the solar system.